Hi everybody, welcome to section 1.1, powers and exponents. In this section, we're going to talk about and make sure that we can write products of repeated powers and evaluate those powers. But we're going to talk about what do all those terms mean and then do some examples. All right, so first of all, remember when you learned to add and you kept adding the same number over and over again and you then learned to multiply? So if you had 3 plus 3 plus 3 plus 3, that became 3 times 4. Repeated addition became multiplication. The number you added times however many times you were adding it. 3 times 4. Either way, you had 12. Well, what happens when you're multiplying the same number over and over and over again? Is there a way to do that that is more compact to write? A different way you could solve it? Well, that's where powers come into play. That really, what it is a power, is a product remember means multiplication, of a repeated factor. Factor is a number that you're multiplying. So here when we have the big number 3 and the little number 4, just to the top and right, that whole thing is called a power. The big number is called the base. We've had power and we have base. And that's the repeated factor, the number you're going to multiply. Then you have 4. That's the exponent. That's the number of times the base is a factor. So the number of times you multiply. Yeah. So really what 3 to the 4th power shows us is 3 times 3 times 3 times 3. And in case you were wondering, the answer to that is 81. We just keep multiplying along. But really what we're saying is 3 is a factor 4 times when we have it written 3 to the 4th power. And whatever it looks like depends on the numbers that are used. 5 to the 3rd power is 5 times 5 times 5. 5 is used 3 different times. All right, now just some other terms that you might hear or wording you may hear if you're not as familiar with powers yet. 4 to the 2nd power can be said 4 squared, and really this is true for any base. I just picked a base number. 4 squared, so when you see a 2, that means squared, or you say it 4 to the 2nd power. Or we have 4 to the 3rd power, 4 was a 3, 4 cubed, which is 4 to the 3rd power. You can say each of these either way, and it's perfectly fine. After that, we just say the base to whatever power. 4 to the 4th power, or 4 to the 5th power, or 4 to the 182nd power, whatever it is. But just make sure you don't say 4 to, 4 4. It's 4 to the whatever power. Now, a lot of times you'll hear teachers like myself or others shortcut and say 4 to the 4th, 4 to the 72nd. The word power is just kind of implied at the end, but you have to have that kind of the to the in there to imply that that's now that second number you say is an exponent, okay? All right, now that we've talked about some of the terminology, now we need to do some examples with these. So the first thing we're going to do is write the product as a power. All we're going to do is shorten it up into a power. So 6 times 6 times 6 times 6 times 6. That means our base number is going to be 6. So whatever number is listed, that's your big number. And then your exponent is, how many times are you multiplying it? 1, 2, 3, 4, 5. So 6 to the 5th power. When we want to write the product as a power, this is what we want. We want a base and an exponent. We don't need the actual answer yet. That comes later. Or over here, 50 times 50 times 50. How many times? What's our base? 50, because that's the number that's being multiplied. How many times are we multiplying it? 1, 2, 3. 50 to the 3rd power. Now, one other thing you'll notice in our problems, in example A, I use the X as a time symbol. Over here, I use the dot, the little dot, as the multiplication symbol. Either one of them means multiplication. Another way you can also write multiplication is using parentheses. So you could even see an example that might look like this. A third one in here. I could have something like this. 7, parentheses, 7, parentheses, another 7. All of these parentheses bumped right up against each other like this all mean multiplication. Now, do you see why we might want to write things as a power? That took up a whole lot of space. So what's my base? Obviously it's 7. I've written it a whole lot of times already. How many times are we multiplying 7? Well, we count carefully. 1, 2, 3, 4, 5, 6, 7, 8, 9. 7 to the 9th power. Well, that's there. That much space versus that much space to write it. Oh boy. I like writing things in powers. Okay, now we have to find the value of the power. So if we have it already written as a power, how do we figure out what is its value? Well, 8 to the 3rd power means we're multiplying 8 3 times. So write that out. What's 8 times 8 times 8? Now, I could sit here and multiply it all out. For the sake of time on the video, I'm pulling out my handy dandy calculator, and I'm going to go 8 times 8 times 8. And I get 512. Really, all we have to do is follow order of operations. What's 8 times 8? That's 64. Now we have 64 times 8. Well, I don't like multiplying it that way. I'd rather turn it. So 64 times 8. 4 times 8 is 32. Carry the 3. 8 times 6 is 48, plus 3 is 51. So 512. So we get it the same way, following order of operations. All right, then we've got 12 squared, which means we're doing 12 times 12. Now, you might know that already, or if you don't, stick in a calculator and multiply it all out, and we get 144. So now we can find the value of the power. We can find the actual number that 8 to the 3rd, 12 to the 2nd, or if we took the time, 6 to the 5th, 50 to the 30th, or 50 to the 3rd, or 7 to the 9th represents. All right, a few more examples, a few more things to talk about. So we're talking about exponents and powers and all that kind of stuff. We need to talk about perfect squares. So numbers that are the answer when you multiply a number times itself. Take something to the 2nd power. All comes off the idea of a square. Remember, squares, they have right angles. All their sides are the same length. And it'd be like dividing this one up. Let's say it's 2 centimeters in length. Well, each side is 2 centimeters. Well, if I split each side exactly in half, how long is each little side? 1 centimeter and 1 centimeter. Each little part is 1 centimeter, correct? Hopefully you're all agreeing with me. So they're all 1 centimeter by 1 centimeter. The area of a square is is length times width. They're the sides squared, right? That's 1 times 1. 1. So the area here is 1 centimeter squared, centimeter squared. I know I'm lacking space. Altogether, what is that total? 1, 2, 3, 4. 4 centimeters squared. Or the other way we look at it, we say area is the whole side length times the whole side length. 2 centimeters times 2 centimeters. Well, multiply your numbers. 2 times 2. That's 4. Also known as 2 squared. And then we do centimeter times centimeter. Each unit gets measured or multiplied by itself. We just write that as centimeters squared. So 2 squared is 4. So 4 is a perfect square because some number times itself gives me 4. So when we're talking perfect squares, we're saying what number times itself gives me this number. A number times itself, perfect squares, a number times itself. So here you can put this into your notes, a list of the perfect squares up through 12. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared 9. 4 squared 16. 5 squared 25. 6 squared 36. 7 squared 49. 8 squared, 64. 9 squared, 81. 10 squared, 100. 11 squared, 121. 12 squared, 144. So then you can ask, is a certain number a perfect square? Does it fall in this list? Or if you kept going, would it fall in that list? Well, is 50 a perfect square? Is 50 on this list? Nope, it'd be right there after 49. Oh, it's not there. So 50 is not a perfect square. No. What about 9? Oh yeah, we see it right there. So yes, it is. There aren't a lot of perfect squares. There's a lot of things in between. And eventually you'll learn about something called square roots, which help us break down these perfect squares. And we say what number to the second power gives us our perfect square. So the fact that it's like 8 squared. That sort of thing. You'll learn much more about that when you get into 8th grade math. All right, last kind of application problem here. A baseball diamond, so this is for all you baseball fans, a baseball diamond is a square with sides of 90 feet. Square, 90 feet. What is the area of a baseball diamond? Well, here's my best attempt at drawing a baseball diamond. 90 feet, 90 feet. What do? Oh, we've got a square 90, don't we? What's 90 squared? And of course, the units will go on at the end. Well, I could pull out my handy dandy calculator, or I could just say, what's 90 times 90? And you all know the trick when you're multiplying with zeros, right? Ignore those for a second. What's 9 times 9? It's 9 squared, in other words. It's 81. And then we just stick the zeros on the end. So 8,100 feet squared is the area of a baseball diamond. All right, so we've wrapped up and talked about how we can write products as repeated products of repeated powers, and evaluating or saying what's the actual value of that power. All right, thanks for watching.